Good morning. Happy St. Patrick's Day to those of you from groups in that part of the world. My name's Steve Croft. I am a researcher in the Department of Astronomy here on campus. I see many familiar faces here, but as I often do, I'd like to ask you to raise your hand if this is your first Science at Cal lecture. Wow, okay, welcome. Please sign up for our mailing list. We have these events going on the third Saturday of every month. There's a lot of other things going on campus. There's also some flyers at the back here with a couple of other upcoming events that are sort of under the Science at Cal umbrella. There's the 2012 Lawson lecture by Bill Ellsworth from the US Geological Survey on earthquakes in Sutarja Dye Hall, which those of you who remember the science festival that we did here in January of last year. 2011. Is that long ago, Rachel? That was over there. We're going to be doing another science festival, part of the Bay Area Science Festival later this year in October. I think the dates remain to be sort of absolutely fixed on that. There's also a few spaces left for this vast and undetectable event at the San Francisco Arts Commission Gallery, taking place on March 21st. Although it says RSVP by March 16th on here, you can still RSVP. There are a few places left, and it's sort of a dialogue on science and art and on the visual language that scientists and artists use to communicate. And there's also a flyer about the exhibit itself, sort of a small exhibit. It's right by City Hall, so some of you may wish to check that out. I mentioned we have lectures on the third Saturday of every month. There's an exception to every rule, and next month is Cal Day, when we're not going to be here in this room with a science lecture at 11, but I still encourage you to come to campus and check out the Cal Day website. If you Google Cal Day, it'll probably be the first thing that comes up, and it's the big campus open house. Many of you have probably been to this. The UC Museum of Paleontology will be open. I think it's 1 or maybe 2 days a year that you can go there and sort of get a tour there. The astronomy department will be out in our new home down near Sproul Plaza at Photosphere, but we'll have some solar telescopes out on the near Sproul Hall. There's just going to be a ton of stuff going on campus, a lot of stuff for all the family at all kinds of levels. Really encourage you to come and check that out. And then back again, third Saturday of the month in here on May, whatever that is. Look it up. May 19th. Professor Ruth Tringham, who's an archaeologist here, is going to talk about reconciling science and the imagination in the construction of the deep prehistoric past. So how do we find out about deep time, basically, from archaeology, and I think that'll be kind of a neat sort of, again, kind of blending of science and sort of more of the humanities too. Living here in the Bay Area, I guess we get used to seeing lots of sunshine, although in the past week you may have forgotten what it looks like. Dr. Hazel Bain is here today to remind you, and perhaps also to open your eyes to aspects of the sun that you may not have considered. She did her undergrad and PhD at the University of Glasgow in Scotland, or Glasgow, as I guess people pronounce it around here. Yes. And she's been at the Space Sciences Laboratory a couple of years, and is going to be telling us about the sun, star, and our back here. That's what Dr. Bain. Thank you.
Yeah, so I guess the reason as Steve mentioned, I'm from Scotland. Oh, I should turn this on. The reason that I study the sun in Glasgow is because it's the only way we get to see the sun is through some NASA instrument or something. It's always cloudy and rainy. And I guess I've become a bit too climatised to California because the last week I found it cold, and I've been told by people from home that I've now become soft. This is a summer in Scotland, which is probably true. The sun. So I guess people have always been like mystified by the stars. People look up in the night sky and we see the constellations. The Greeks have lots of stories about their gods and the constellations. Sailors use the stars for navigation, and I guess we kind of forget sometimes that stars are not just a point in the night sky. That our sun is actually a star, and it's right there at the center of our solar system. And so, really, it's a great opportunity to study these kind of objects. What the processes that are going on inside the sun are, and how that affects the surrounding planets around these stars. So, for example, our sun, it really affects our seasons. It changes the weather. It gives photosynthesis in plants. You know, it has a really everyday effect on our lives. If it wasn't for the sun, then the atmosphere wouldn't be warm enough, we wouldn't have liquid water, and we wouldn't have life as we know it. Maybe it exists in some other form, but here on Earth we need liquid water to survive, and we need the sun to keep our atmosphere warm. But there's also the effects of the sun that you don't realise. We really are inside the atmosphere of our own star here, and the magnetic field that comes from the sun really influences our own space environment, and it interacts with our own magnetic field through the solar wind. So I guess this is a very blank first slide, and it's because I wanted to show my first proper slide as being this. This always amazes me. This is the size of Earth in comparison to the sun. The sun is huge. And this, really, up until almost the final draft of my thesis was my first line. The sun is big, because that always gets me. So the sun really, I mean, you can fit 1 million Earths inside the sun. The diameter of the sun is 100 times that of the Earth, and it's something like 300,000 times the mass, which means it's 1 trillion tons. So it's huge. And you can see, really, you know, this is one small feature on the sun here, and that envelops our whole Earth. So that always gets me, how large scale these things are. But where does our sun sit in the grand scheme of stars? And you can see that here by the Hertzsprung-Russell diagram. So this looks quite complicated, but all you really need to know is that on this axis here you have the luminosity, so it's really how bright the star is. And here you have the temperature of the star. Now this is actually kind of counterintuitive. The temperature increases in this direction, so this is really hot, and this is kind of colder. So we have the really high mass stars up here that have really high temperature and are really bright. And then down here we have the cooler, smaller mass stars. And so our sun is actually right in the middle here. So we're kind of average. You know, these things have about 60 times the mass of the sun. These are maybe about 10%. And so what you can see here is that actually these stars up here, they actually live really fast. They have a really short lifetime. How long a star lasts depends on its mass. So these things live fast and die young. And these things have a smaller mass and sort of last much longer. In fact, some of these are expected to have a lifetime longer than what our universe is at right now, the age of the universe. So we're not actually sure what happens to these things down here at the end of their lifetime, because we've not got to that point yet. So actually, you'll see this big stripe down the middle here, and this is called the main sequence. And so when a star is born, it's born out of a big cloud of dust and gas called a nebulae. And then the gas starts to clump through gravity, and you start to get clumps forming. And then once those clumps get denser and the temperature increases, then you start to get nuclear fusion in the center of the sun, and it starts to burn, and you start to get this protostar. And then what really happens at that point really depends on its mass. At that point, it will appear sometime on this main sequence, and it's expected that it will stay there for about 10 billion years. So our sun here is about 4.5 billion years old, so we're only really about halfway through. And once it's finished burning hydrogen in its core, it will finish burning hydrogen, and it'll start to burn helium. And when it does that, it actually moves off the main sequence, and it moves over to the red giant branch here, where the outer layers of the sun will really expand, and they'll blow off. And the outer layers of the sun will actually go beyond the orbit of Mercury, so it's going to be like 200 times the size that it is now. So in several billion years' time, we're going to be inside the sun. And once that happens, once the helium has finally stopped burning, it jumps down here, and it becomes a white dwarf. And it should be about, I think it's about 6% of the mass that's left is down here in the white dwarfs. And then we're not really sure what will happen after that. But that's kind of for sun-like stars. Other stars are more exotic and they do other things, but this is what we think will happen to our sun here. So I wanted to start from the core of the sun and work my way out, all the way out to how it interacts with the Earth. And I've heard this phrase used quite often in talks called peeling the solar onion. And this always makes me think of the film Shrek. And Shrek is explaining to Donkey, he's trying to say, ogres have layers, Donkey. Or ogres are like onions, they have layers. And this always makes me think of that, so we're peeling the solar onion here. So right in the center of the sun is the core. So this is about 1/5 of the radius. It's about, right in the center, really the real core of the sun. And this is where the nuclear fusion happens. And what we see here at Earth, the energy has to get from the core all the way out through the outer layers and out to our sun, out to Earth. But even to get out to the edge of the solar surface out here, this takes about 50 million years. So basically, the energy starts in the core, and you get these photons. So this is just little bundles of energy or light, and they bounce around in here. They keep getting scattered and reabsorbed. So it takes about 50 million years for that energy in the core to get out to this part here, which we call the radiative zone, and then out through the convection zone. And so, really, if the centre of the sun switched off just like that, we wouldn't know about it for 50 million years. We wouldn't start to feel the effects of that for 50 million years. So here, in this outer region, this is just below the solar surface, and it's called the convection zone. And at this point, the energy transfer changes to be like convection. So this is where the plasma takes the heat and transfers it up to the surface. So it's kind of like boiling water. You'll see that you get little bubbles forming in the water, and the hot stuff flows up, and then the cool stuff goes down. And there's this really cool movie. This is from the Big Bear Solar Observatory, and this is actually down just outside Los Angeles, although it's run by the people in New Jersey. But each of these are what we call solar granulation cells. And so each one of these, I think this one down here I worked out to be about 3,000 kilometers in width. So these things are pretty huge. And you can see here, the stuff in the middle bubbles up, that's the hot stuff. And then the dark rims around the outside are where the cool stuff goes along and down, back into the solar interior. So you get this churning motion. So yeah, I just think this is amazing to watch. And people actually do simulations of this, and sometimes you can't actually tell the difference between the simulations and the actual the movie, which is just amazing.
What is the stuff that appears to be sort of
in here?
Yeah.
I'm not entirely sure there. This might be something to do with image processing, actually, that maybe they've enhanced certain bits. It's probably just small parts of well, you get super granulation and small granulation. So basically, these are maybe the big cells, and these are probably smaller little cells where it's bubbling. But I think they're probably enhanced here just because of the image processing to get all these parts out. So, but they're probably small scale granulation in there. So once you get out of the solar interior, we have several layers, and they all look quite different. So if we start at the solar surface, this is really considered to be the photosphere. So if you look at the sun, well, not with your eyes because you shouldn't do that, but if you're just to see the sun through, without having any filters or anything, what you'll see is the photosphere. And I'll come back to that in a minute, but above the photosphere is the chromosphere. And the chromosphere, that's actually where the temperature is a minimum. So from the solar interior, the temperature slowly decreases until you get to the chromosphere, and there's like a temperature minimum in there. And what's really weird is that once you get to the corona, the temperature increases again. So in the chromosphere, it's about a few thousand degrees. By the time you get to the corona, it's gone back up to 1,000,000 degrees, and we don't really understand why that happens. You would think that would be something that we would know, but there's been competing theories of why that's the case, and I'll go into a bit more about that later. But basically, the point of this slide is to show that basically there's different layers, and they look a bit different as you go up. And the reason for that is the magnetic field. So, actually I should go back, so I don't want to show you this just yet until I've explained it. The magnetic field is generated in the solar interior. And what you actually see on the surface is that the equatorial range of the sun, this part in the middle here, that actually rotates faster than at the poles. So it takes about 27 days for a feature on the sun at the equator to go across the disk. Or to rotate around the disk, whilst at the poles it takes about 34 days. So you get this stuff in the middle moving faster. So it's a little bit like a stream. The stuff in the middle of the stream moves faster than the stuff at the side. And the effect of that is when the magnetic field is generated in the core, basically the center or the equatorial part of the sun twists the field, and so it starts getting more and more complicated. And so you can see that here. So here's the sun. Here's it rotating, here's the magnetic field lines, and they start to twist. And as that happens, they get more and more tangled, and you'll start to see they become unstable. So that's where you get all these crazy features going on in the sun. Yeah, crazy features. Here we go again. So, you'll see that it starts to get bunched up here, and then start to see these loops appearing, and the whole thing becomes unstable. And so these, I'll show you the next movie first before I come back to the next thing. So here we go. This is the part where the field goes unstable. So we're now going into the solar interior, and you can see these white lines here represent the magnetic field, and they start to rise and push through the photosphere. Okay, so you start to see these field lines coming through, and you'll see these two black spots on the photosphere here. There we go. And so you start to see different parts of field lines all over the sun, and that's what gives it our different structure, the different layers. So you're seeing different parts of the field, you're seeing different temperatures and different things like that. And so what these black spots are actually called sunspots. And if you're to look at them up close, then you can see there's this dark part in the middle here, followed by this part around about here. So the dark part in here is called the umbra, and this is the penumbra. And the reason this is dark in the middle, here the magnetic field is so strong that it actually prevents that hot material rising. It prevents the convection bringing the hot material up, so it appears dark. And then this stuff here, the magnetic field is kind of horizontal. In here it's sort of vertical. So you don't, convection is sort of happening round about here again, but you just really don't see anything in the middle here.
Is that cooler?
Yes, I think it is, actually. I forget what temperature it is. But on the photosphere you're looking at about 5,700 Kelvin or something like that for the photosphere. And what you can see here is that they come up in pairs, so are sort of complex sunspot pairs. So you can see here a few. And what actually happens in the sunspots is that they start high up in latitude and they move towards the equator as the field gets twisted. So they start high and then move towards the equator. And it's actually when they come up and they're really what we call, and this is a technical term, when they're big, bad and ugly, that's when we start to get flares. So that's when you get the really twisted field and you start to see really complex regions like this. When we see something like that, if you're a flare solar physicist, you start to get excited. And that's, I don't know if you've been noticing in the news recently that there was a lot of flares happening in the last week. Yeah, we had a sunspot region that came up and we looked at it and we were like, wow, this is going to be a good one. And so you start, the bigger, the badder and the uglier that they are, then the more interesting they are for us. Well, for me. Maybe there's people who study the quiet sun who don't.
A question, what's the difference between the top and the bottom rectangle?
Well, what, do you mean just the...
Well, I mean, you're showing two different things.
Yeah. So this one here. So first of all, these are both images taken with the Nancay spacecraft.
And they're different.
Yes. So do you just mean the structure? So for instance, this one is just a very simple sunspot region, whereas this one down here has kind of a little bit of added other sort of, what do you call them? I guess they're just smaller sunspots.
Yeah, so you've got a simple sunspot and a complicated.
Yes. So this is what I mean. Once it starts to get big and bad and ugly. So basically, you'll see these things here, and actually, what happens is the field in here gets sheared, so it gets twisted. And I think in this particular sunspot, there was a flare happened right along the middle here, because the field lines are coming out of the sunspot. They come out of one sunspot and they go into the other. So one's positive polarity and one's negative polarity. And if you have lots of these smaller features here, you know, the field is coming out, and so you get lots of different connections happening across different sunspots. And when it starts to get what we call mixed polarity, so I can show that in the next movie, that's when the field starts to get really twisted with itself, and that's when it gets towards flare conditions. So this is a movie, and it's actually taken with the new Solar Dynamics Observatory spacecraft, and they have an instrument on there that measures the magnetic field here. So what you're seeing is there's going to be an active regional form right here. So the white and the dark are the different polarities. So one's positive, one's negative. And you'll see there's lots of sort of small scale parts of the magnetic field, and then you start to see it bubbling up. So I think the white is positive and black is negative, and you'll see that you start to get, I think, these are one sunspot, there's another one over here, and you can see that the white and dark are really mixed. So that's what you're seeing in the previous image. You're seeing smaller features of the sunspot here. And when you start to get this mixed polarity, so mixed white and black, that's when it becomes big, bad and ugly. So you'll see there's parts of white in here, there's a huge big white thing here, there's smaller bits of black in there, and this here is what we call ugly. And this particular active region, I think, produced quite a big flare last year. It was what we call the Valentine's Day flare. We seem to like to label all of our flares by simple names. So when you get this mixed field, that's when you get flare-like conditions.
Is this real time or speeded up?
This is speeded up. So that would have taken about, that's the full passage across the disk. So here it's on one side on the limb, and it forms and takes about maybe 27 days-ish. Well, no, it probably takes about 2 weeks to cross the field, cross the disk.
So those black areas like a seam?
So the black areas, so when I showed the movie of the field coming through the photosphere, the black isn't actually going down, it's just showing you where the positive. So do you remember, this is a slide I actually have later, you know when you get bar magnets, and you have a positive and a negative, a north and a south on the magnets. This is the north and the south, so black is like south and the white is the north of the magnetic field. So you get field coming out, it'll probably come out of here, loop around and go back down in the black. So it's just showing you.
Three-dimensional there.
Yeah, I guess it does look a little bit. There's issues about right in the centre, I think, here, because what you're actually seeing, I think, on MDI, I think this is just a picture of the magnetic field pointing directly towards you, so the field tilts in different directions, so there's issues about that there, but yeah, what you're seeing basically is the field coming out and going back in. But you're not actually seeing, well, I guess you are seeing a bit further down, but these are just magnetogram images, whereas in the white light image from before, I guess you're seeing a bit further down.
But it's coming out a long way.
Yeah.
To us.
Yeah. Well, okay, yes and no. I'll come back to that. There's a really nice slide coming up in a minute. So these sunspots actually have a cycle. So I don't know if you've heard of the solar cycle. Maybe that's been in the news recently. And it lasts about 11 years. And what we see is that sunspots, so each of one of these is a solar cycle. And this is what we call the butterfly diagram, just because it looks like a nice butterfly. And these are where the sunspots lie on the sun. So this is the North Pole, and this is the South Pole, and this line along here is the equator. Oops, that's the equator there. And so what I said about the sunspots forming at really high latitudes and then moving to the center, to the equator. So here we see them forming at high latitudes, and they moved to the equator on both sides, in both hemispheres. So, and you can see that the number of sunspots has a periodic cycle as well. So the number of sunspots increases in each of these. And the time that it takes to go from like here to the next part here is about 11 years. Okay, so we go through periods of maximum and minimum. So right at the start, like that animation where the field lines were just lying straight, that's solar minimum, everything's very quiet, it's not very interesting for flare people. Then the field gets really tangled and twisted, and you start to get flares, and you start to get sunspots, and they move closer to the equator, and that's when you get all the big flares. So the 11-year cycle there's actually a 22-year cycle. So the 11-year cycle are these sunspots moving towards the equator. And that actually, every 2 years, the north and the south pole of the magnetic field switch. So like in here, when we're on Earth, we have a north pole and a south pole. And on the sun, that actually switches every 22 years. So we have an 11-year sunspot cycle, but a 22-year magnetic cycle. And there's also a hint, people are not really sure about this, whether there's an overall, we have a really high solar maximum and then a lower maximum down here, that there might be some sort of maybe 100, 200-year cycle where it's, you get really big flares and lots of activity, which maybe around about here, and then maybe these solar cycles are a little bit less active. But that's unclear right now.
Question about that data.
Yeah.
So, in the 1800s, it appears that it was lower activity, but would that be a matter of the accuracy of our data? Or our ability to see?
Possibly. I'm not sure actually. I think there's other ways you can work out what the solar activity was, because you can see the effects here on Earth. So they might not have calculated it from the exact observations. How far back do these go? Well, actually no, because back in the 1800s, I think the first solar flare was seen in the 1800s. So I mean, they probably were actually taking sunspot measurements back there. So that probably is still quite accurate. The weird thing is this one, we're down here, and the weird thing is that it took us longer to get out of when we came out of the last solar maximum down here. it actually took longer for this cycle to start. We expected it to start a few years ago. I was really hoping that the solar maximum would come at the end of my PhD, which was 2 years ago, and I was thinking, oh great, I'll get some brilliant flares, because as a flare scientist, I started in solar minimum, so there was no new flares for me to look at, and it actually took really until the last maybe year or so, to now really, to start getting the big flares coming out. So we don't really understand everything there is to know about the solar cycle, and people try to predict how big the next solar cycle is going to be, how many big flares we're going to have, and I think very few people get it completely right. I think it's a large part of guesswork in some ways. This one is surprises, so we'll see what happens as it continues.
What are the blue bars on that?
I think it's just to show that the peak in the sun, in the number of sunspots, really happens around about here. So what we actually find is we get the most, or the biggest flares really kind of in the decay phase of each solar cycle. So this is just to show that that's coming from that particular region here, that although the sunspot cycle ramps up and down, that you still see the sunspots for quite a bit in the decay. It was just this particular figure was the one nice figure that I could find that actually showed beyond 2010. A lot of the figures that I found stopped right here, and I was like, I really want to show that we picked up that you start to get this solar cycle starting up here. So this shows what the sun is going to look like through solar minimum to solar maximum, back down to solar minimum. So you can see way back in 1986 that the sun was really quite quiet looking. It's quite simple. It was all what we consider quiet sun conditions. And then as the years went on, you start to see these active regions. So these are where the sunspots are and where the really complicated magnetic field is. And you start to see that there's quite a lot more of them. And then they start to decline slowly, and then you're back to solar minimum again. And one thing I'd like to point out that you can see here that these images are not that great. So I'll show you later some of the new images coming from the new Solar Dynamics Observatory. But this is a great picture for showing the solar cycle, because the new instruments haven't been up there long enough to see the whole quiet max and then quiet again. So. But yeah, you can see that you can just make out that there's active regions there, but the new images that we get are just spectacular.
This ultraviolet.
Yes. Yeah.
How is it that the magnetic field becomes detangled?
Detangled.
Yeah, how it's all tangled at first and it calms down. How does it detangle itself?
Well, it rearranges itself. That's where you get the flares. So what's happening is that it gets twisted up and then it becomes unstable, and it can't exist in that really complicated state for too long. So it starts to have solar flares, and it starts to go, basically a solar flare, in simple terms, is the magnetic field rearranging itself from a very complex configuration with lots of energy stored into it to something simple. So it's like, I guess a very simple analogy is like an elastic band. You twist it, you twist it, twist it, you store lots and lots of energy, it's really twisted, and you let it go. And it converts the energy in the band into, I guess heat or sound or whatever, the motion. And that's really what happens in solar flares, is you're releasing some of the energy that's stored in the magnetic field, and it goes back to a lower state. So that's really kind of what's happening, is where you see all these things. So this again is the quiet sun over here, and then this is the active sun. So you can see there's some flares going off here. There's lots of active regions. You can't. This is extreme ultraviolet. Yes. This was from the NASA ESA mission, the SOHO mission, and this is EIT. So these are kind of older images now, but again they show the differences between the solar and the solar maximum and solar minimum. One thing I'd like to point out here, you might notice there's a sort of darker region up round about here. These things are called coronal holes, and in solar minimum they tend to be up round about here, but in the maximum they can come down and they actually extend into the main disk of the flare. And that's where in these active regions the loops are very large, and they connect from one sunspot to another. Out here they actually go straight out into the interplanetary field, so they're what we call open magnetic fields. So they actually join with the interplanetary medium, and that's like the source of where we get some of the solar wind, and so that's where those things are coming from. But as it gets more complicated, those coronal holes start to move onto the disk. So yeah, this is my slide. That maybe I should have put that earlier on. this is like your normal bar magnet. So you have your north and your south and your field lines. So I don't remember, we had to do this in school, and you got iron filings, and you had to, you know, sprinkle your iron filings over the magnet, and you got to be able to see where the field lines traced out. And so you can't actually see the magnetic field itself, but you can infer that it's there just from watching where these iron filings are. And so that's what we see in the corona. So basically the plasma in the corona is stuck onto the magnetic field lines. So what we're doing is we're tracing out where those loops are. And you can see they emerge from the photosphere here, they go up, and then they go back down into the photosphere. And that's like where those sunspots were. So you're getting this field coming up and looping around and coming out. And you can see how complicated it is. I mean, it's not as simple as those animations that you just get a field popping up and then it's there. These things are complicated. You get them joining here, there's some parts joining over there, there's, you know, they're all over the place. And that's what I mean when it's big, bad and ugly, when it's twisted and confused. That's when the energy is all stored in the magnetic field and it's ready to get out. It's just waiting for something to happen, and then bam, a solar flare will go off.
What's happening in the field that causes these lines?
These lines here.
Yeah.
So to try and make it simple, below the photosphere, basically the plasma is stuck onto the field, and the rotation of the plasma pulls the field. In the corona, the plasma tells the magnetic, or the plasma tells the magnetic field where to go. So what's actually happening is that you're tracing out these field lines, and there's probably like hot electrons, for example. These are probably about a few megakelvin, a few million degrees in temperature, and so what you're seeing is the electrons and everything along these field lines brighten up, and that's what you're seeing. You're actually seeing them emit because they're hot. And so the reason we can actually see this, you can't see this with your eyes, but you can see it with EUV filters. So that's why we put up these spacecraft like TRACE and the new XDO one, and they have filters on it to basically just look at the EUV emission coming from these things.
What is the definition of plasma?
Okay, so it's basically the electrons and the ions. So in this case, we talk a lot about electrons. So the electrons here are stuck on the magnetic field line. So basically they spiral around it. So these ones here are basically showing hot electrons, and actually there'll probably be a lot of iron up here as well. So in the corona, when they first looked at the corona, they thought, what is this substance that we're seeing? Because they could see something there that they didn't understand what it was, and the only way you could get this spectroscopy, basically they were seeing this substance on the sun and they were like, this must be a new substance, and they called what they could see in the corona coronium. And what it actually turned out to be was iron, because they couldn't, from the periodic table that they have now, they couldn't work out how you could get anything so hot as to be able to see these lines. And the reason that you're actually seeing this is it's actually iron. And so when we say that the iron is ionized, you've got an iron atom, so it has its nucleus and it has all its protons and neutrons in the middle, and then the electrons spin around. And when it becomes ionized, basically the electrons get energy from the sun, and they get energized so fast that they basically leave the atom. They're able to leave it, and when that happens, you say that it's ionized. And so if you have iron 1, then it means it's lost one of its electrons. If you have iron 2, it's lost 2. And this stuff, I believe, is iron 13. So it's got to be really hot for those electrons to leave the atoms. And so what you're seeing here is really hot material, really hot iron, and you're seeing the emission from that thing, from that atom.
Did you say iron 30?
Iron 13, I think it is. Yeah.
Can you tell which side's going up and which side's going back down?
So that's why we look at the what we call magnetograms. So that black and white image from before, if you take an image of the sun, then you can see which one's black and which one's white, so you can see where the positive and negative are. And that's what a lot of people do. They actually study those magnetograms to see where the positive and negative field are, where the north and the south is, so they can work out what's happening in the flare, because what you see is the white bits moving into the dark, and then the dark moving into the white, and then they cancel each other out and things. So yeah, you can see it. So what we do is we combine these kind of images with the magnetograms, and you lay them on top of each other. They're sometimes taken by different spacecraft, sometimes the same spacecraft has two different instruments on it. So the Solar Dynamics Observatory has one instrument called the Atmospheric Imaging Assembly. So if you're looking for anything on the web, that's the thing to look for. There's amazing images from there. And they take these kind of images, so they have lots of different filters. They have 7 different filters that you can take, and you see images like this. And then they have HMI, which takes the magnetogram. So you look at the images here, and then you look at the images on the magnetogram, and you can join them together and see what's happening in the photosphere, where the field is coming out the solar interior, and you can look in the corona with AIA.
If you just take the time sequence, you can notice which way the material is moving.
Yes, you can. You can. So what actually happens is, I think there's the magnetic field in the photosphere is not really my area as such, but you can see that the black and white come together, and quite often they sort of cancel each other out and they disappear, and it's called flux cancellation. So you get flux emergence, where it comes out and it separates into positive and negative, and you get them coming together and cancelling each other out.
Is there any relay to those colours? Or
no, not really. So this is something that we do as solar scientists. We basically each of the filters we tend to give a colour table to, just so that we can pull out some of the features. And sometimes you'll use maybe a green or a blue or something, just because it brings out nicer features. Like it's kind of a preference thing. But certainly, different instruments tend to keep similar colour tables for each filter, so that when you look at images, you can kind of say, oh, that's green, that's probably EIT, or blue is something else. So.
How many Tesla is there in the service?
How many what? Sorry.
Tesla.
We don't work in Tesla. We work in Gauss. So it's 2,000 Gauss inside a sunspot region. Probably down around about the foot points here. So, and then up round about here, we're not really sure actually the exact value of it, but it's probably around about maybe somewhere between a 10 and 100 Gauss. So whatever the conversion to Gauss is, I forget. But the thing is, we don't actually know what the magnetic field strength is up in the corona, because measuring that is incredibly difficult. And that's one of the things that people are really trying to work out. So what they actually do is use the magnetogram data, so the black and the white spots data. They can work out the strength down on the photosphere, and then they use models and equations to basically work out what the field lines should be. But the thing is, it's much more complicated than what our models sometimes can tell us. So yeah, it's a bit of guesswork.
Do you listen to the cyclotron frequency of that? Electron?
Yeah, so you can. So yes, so you can do. So this may be a bit too complicated, but basically the electrons are spiraling around the magnetic field, and when they do that, they actually give off energy. They give off photons, and you actually get radio emission coming out. And so for the sun, basically the frequency that you see the radio emission at is related to the magnetic field strength for the gyro frequency. So you can work out what the magnetic field is from the radio data. The problem is that because you have lots of different field lines, and they're all slightly different like values of magnetic field, that they all kind of merge together, and it's actually really difficult to make those observations. And there's another big push right now for us to get more radio interferometers. So to do these kind of observations, we do them on the ground. We have ground-based interferometers and observatories that do the radio data, but we don't actually have the spectral resolution. We don't take it at fine enough frequencies to be able to see those features in the spectrum. And there's been a big push really to try and get observations of that kind. And I'm a big supporter. I really would like those kind of observations. And I think that's going to happen soon, maybe in the next 10, 20 years, hopefully, if the funding is there for it, to get an instrument that will be able to tell us really what's going on down in this part, down here.
What are those radio frequencies?
So for the sun, for down at the foot points of the loops down here, you're looking at like maybe gigahertz, so 30 gigahertz, 17 gigahertz. To see the gyro frequency stuff, you're looking around about 1 gigahertz, I think, for active regions for flares. And what you should actually see is it should look like a triangle type spectrum. So you'll see, as it goes up in frequency, you'll see a peak, and where you see these gyro frequency things, you actually see dips in the spectrum. We just don't have the resolution right now. I think there's a couple of, if you look at there's an observatory in Japan that takes images at 34 and 17 gigahertz. There's but they don't actually have, and they don't always have images as well. That's the other thing. So some places have images and radio emission, some places just have the spectrum, and so there's a lot still to be done in that area. But yeah, that's quite complex. I'll stay clear of that right now. But there's different frequencies depending where you are in the world. There's different observatories that go anywhere from probably about 20 megahertz up to the gigahertz, and then below that we really have to be taking the observations in space. So in the kilohertz frequencies, it all comes from spacecraft. So again, this is the corona. So what we were seeing here is really just the flaring loops, and these are quite sort of, they're huge, but they're still quite low down. But during solar eclipses, and this is actually the moon that's in the middle here, you actually see that the coronal field extends way out into the interplanetary medium, and you can see that you get these things, we call them streamers, and these sort of exist above the active regions, and you can see that all the field actually just extends right out. These images are amazing. I think they require quite a lot of processing of the images. I should say that these are taken on Earth here. They're people who hunt eclipses, and they basically go and find solar eclipses, and they try and take these amazing photos. And but yeah, you can see that you see the open field down here from the coronal poles. You can see the streamers, and this is all extending out into what we call the heliosphere, and it interacts with the solar magnetic field and things like that.
Do those streamers have radio frequencies on those rotating?
I guess they must do. Yeah, I'm not sure actually.
Do we receive those at all here on Earth?
Do we? What? Sorry.
The radio frequencies. Do we get those here on Earth?
Yes. So yeah, you can. We actually put spacecraft up there to see the lower frequency stuff as it approaches Earth, and then we can also see the radio emission from the sun, from the ground-based, from the higher frequencies. So yeah, these images are just amazing. I love looking at these ones. Okay, so this is kind of out of order because some of the questions actually, but basically the idea is that we can look at different layers in the sun. So we can look at the photosphere using visible light here. We can look at the corona using the UV. This is actually the radio frequencies here, so it's microwaves. So this is actually an image, I think, at 34 gigahertz. And so this is actually taken from the observatory in Japan called Nobeyama. And so you can see here's the X-rays here, and you can see that you see different features. So in the photosphere, we're really seeing these sunspot features. In the corona, we're starting to see the active regions. In UV, we're seeing the bit in between, and then the microwaves is seeing sort of these active regions as well. So the best way to show that is really this movie here. Here's the sunspots, and if you keep your eye on this thing here, you start to see the active region in the UV. So we're back to the photosphere, this is visible, and then this is ultraviolet, and you can see that this is higher up. This is probably somewhere in the just below the corona in the transition region. And there we have X-rays, and you're really starting to see these loops. So the idea here is if you look at different frequencies in the electromagnetic spectrum, you're starting to see different temperatures, and therefore we're seeing different layers. And that's what we try to do. We try to take the photosphere with the magnetic field and the visible light. We try to look in the chromosphere and in the transition region and in the corona in some respects as well with the EUV and the UV images, and then you can also see the X-ray stuff as well. And we're seeing different temperatures, and we can tell what's going on in the flares and in the sun from the different temperatures and wavelengths. And we can actually join them together, and so you're really seeing different temperatures. So you're seeing dark holes here, you're seeing red parts in here, and these all correspond to different temperatures, and you're starting to see the different features at different heights in the sun. And so we use these images to really work out what kind of atoms, what kind of elements, and what kind of plasma is there, what temperature it's at, what's happening to the electrons, how it's moving. This image actually makes me feel a little bit sick. I actually don't like the colour scheme in this, and I sat for my entire PhD with a big poster of this image right next to my head. But so this one I really dislike. So this is a solar flare. So this is when the field gets really twisted and angry, and you start to see these amazing transformations. So what happens is, in a very simple term, the field line are sitting there, they're complicated, and then they break open and they rejoin with other field lines elsewhere. And when they do that, they give off some of their energy, they heat the plasma, they accelerate electrons and ions, and they reform in a state that's in lower energy. So, so this is what happens in solar flares. So first of all, what you see is the main release of energy. Wait till it goes back around again. So you get to see these foot points first of all, and then you start to see the plasma heating up in big loops around about here. This one is called the Bastille Day flare, and it's one of the famous ones that a lot of people have studied, and it's one of the nicest examples, even though it's over 12 years ago now. But yeah, initially you start to see the foot points, which you'll see along here, these really bright things, and those are low down in the atmosphere, and then you see these loops which start to expand up into the corona, and they're really hot, and that's why we can see them at the UV wavelengths. And so this is kind of not very clear, but this is actually a still from an image that I'll show later on, and I just wanted to show it now because this is the solar limb. So this is sun, this is out in the interplanetary medium, and what you're seeing here is there's some loops in here. And this is specifically what I studied. This is why I wanted to show it. And we use this spacecraft called, well, it was originally called HESSI, but it's been renamed RHESSI after one of the scientists that was involved. But they built this instrument here at the lab, here at up the hill at the Space Sciences Lab. And what it does is it looks for X-rays, and it sees them up here next to the loops where the material is really hot. And you see down here where the blue spots are, it's where you get the really high energy X-rays. And this stuff is coming because the plasma's hot, and this stuff is because electrons are being accelerated high up in the corona, up here in the loops. And when they fly down the magnetic field lines, they spiral round, and that's when you get your radio emission. And when they get to the chromosphere, they slam into the chromosphere, and you basically get these hard X-ray emissions. So what we can do is we can actually look at these blue parts, and we can work out how the energy is released in flares, how it accelerates the particles. You can look at the stuff up here, and you can tell how hot it is. So you know what fraction of the flare's energy is going into heating, you know what fraction is going into the acceleration of the particles. And yes, this is just really interesting stuff for me to look at. Okay, this is the Solar Dynamics Observatory, as I was mentioning earlier. And this was one of the first images that we got back from it. So you can see how much better these images are from what we had just 10 years ago. This here is actually an active region, and you can see here this is actually a prominence, and I'll come back to them later. But if you're looking for images if you go on to YouTube, you'll find some amazing flare videos coming from this new instrument. In particular, so it's Solar Dynamics Observatory, and this instrument here is AIA, is the Atmospheric Imaging Assembly. But this was one of the first ones that came out, and it was just like, wow, that's amazing.
How is the flare different from those loops?
These loops here, so the flare, some flares, I'll come to that actually. I have a part on that. So here's another one of the images from the SDO, and this is just crazy. This is another one that happened last year, and all of this material is just sitting there. It just gets blown up into the corona, and then for some reason it just starts to fall back down. This is what we call, so some flares have CMEs, coronal mass ejections, associated with them. So low down the flare happens, and you see all these coronal loops and things. But sometimes, if you have a really big flare, then sometimes you get a coronal mass ejection, and in that flare, lots of plasma is ejected out into the interplanetary medium and starts to come towards Earth. And so that happens as a result of these things here. So this thing, the CME starts off as things like this. So these are called prominences, or filaments. It depends. They were named a long time ago. They're actually called prominences if they're on the limb and you can see the loops, and they're called filaments if you see them on the disk and they're dark. But these things start to be ejected out, and you see the field lines breaking open and the plasma being thrown out. And sometimes it doesn't completely eject. Sometimes you just see the prominence kind of going up, and then it falls back down. And you'll see the effects of the full CME in a minute. So this one is just crazy. I mean, this is the combination of all the different wavelengths. And this material is just thrown up into the atmosphere, but then some of it just starts to fall back down, and you can actually see it impacting down in the chromosphere. You can actually see it. Oh, actually, maybe it's this one. You can see it coming back down and hitting back into the chromosphere. So this happened about maybe 6 months ago, I think, maybe almost a year ago, and I haven't seen any papers from it yet. So there will be a lot of people studying this, to the different parts of it, to see what's going on and to try and understand how that energy was released and how it's thrown out. And here's just more prominences and filaments. So this is what I was saying, they appear black on the surface, or dark, and then they appear these bright things out here, and they're called prominences here and filaments here. But that's just the way they named them when they first were looking at the sun. They didn't realise they were the same things. and you can see that the field, these things still trace out the field lines here. So when they are actually ejected, so this here is the sun, right in the middle, and this is what we call a chronograph image. So it's kind of similar to what happens in an eclipse. You block out the main bright part of the sun, so you can see this fainter stuff around out here. And this was taken in space by the Glasgow spacecraft. So here's the sun, and here's this coronal mass ejection. This is all the plasma that's been thrown out from the flare. So you can see there's different parts of it. There's usually this outer part here that we call the front of the CME. There's this part that we call the cavity, and this bright part in here that's called, usually comes from the filaments. That's that big loop that you see. That's that same material that's in here as it starts to move out. And I once tried to make my own chronograph when I had the chance to go to Hawaii for summer school. Up on Mauna Kea is one of the best observing sites in the world for looking at the sun because it's so clear, and there's really great seeing conditions for the telescopes. I think my stick, dime and chewing gum chronograph wasn't as good as some of the ones you see in a spacecraft, but before doing anything like that, I advise using some solar sunglasses to look at the sun before you hurt your eyes. But yeah. So anyway, this is the same idea. So you have a chronograph here, and then you see the CME ejected. So here it's coming out down here, and there's another one over here. And all this fuzz are basically particles that are accelerated when the CME goes off, and that's them hitting the spacecraft, and you can see the effect that they have. So you can see that these CMEs, they actually have a real impact on on us here on Earth, and also on the satellites that are up in space right now. And so that's why it's kind of important to study these things, because all these crazy white things here are the effects of these energetic particles. And I don't know if you've heard that coronal mass ejections sometimes they cause radio blackouts, they cause power surges in communication lines and long wires and things like that. It's very dangerous for astronauts to be exposed to this kind of thing. If there's going to be a CME, I think they believe they put them in some kind of capsule or chamber or something to stop them being subjected to all these high energy particles. So this one's a little bit further out, so it shows a larger field of view. So here again you can see the occulting disk, and you can see the white light chronograph. These things in the background are actually all stars, because we're actually going around orbiting the sun. And you can see there's quite a lot of solar activity, lots of CMEs coming out. I think at solar maximum you can get, tens of CMEs a day kind of level. So
What's that say in the lower left?
this here, this little here. Actually, this is the little piece that holds the occulting disk in place. So it's similar to my stick and dime. So that just keeps this little bit of metal in there, and it holds it in place. So usually they try and remove the effects of that just so it doesn't get in the way. And these things actually also catch comets, which is just kind of a nice side effect. And you'll see that the comet tail changes direction. So the comet tail is flowing back here because of solar wind, and then it gets blown off and you see it form in the other direction. So sometimes comets actually have two tails, one caused by the solar wind and the other one caused by the direction of the comet itself. So yeah, it's quite a lot of... Recently there's been a bit of publicity about one of the ones that the comet was actually seen. It was what we call a sun-grazing comet, so it flies really close to the sun, and when it gets close to the corona, there's a question about whether how the corona affects the comet, whether it will all burn up before it eventually hits the sun or not. So, how are we doing for time? Okay, so this is the movie. This is putting everything together. So this is taking the CMEs from the chronographs far out, and then you're getting closer to the sun. Then you start to see the EUV corona. Here we see the X-rays that we were seeing with RHESSI up here, and then you start to see the higher energy ones down here. And so this is how we can put it all together. So here's a flare, here's the CME propagating towards Earth. All this snow is the energetic particles that really are impacting the spacecraft. And so this is what we really want to look at, is how things happen in the sun, how they propagate out, and how they affect the Earth.
But in addition, the magnetic field is, in a way, independent of what you've just been showing.
No, the magnetic field actually is, so when the CME goes off, the magnetic field is twisted up amongst that material, so that it actually gets...
Well, they interact, yes.
Yes.
But I mean, you didn't show us the magnetic field.
No, you can't see the magnetic field. You can only really see that if it's hot or something like that. So I guess, let me go back.
Did the orbits of the comets get changed by the interaction with the flares?
Unsure. I don't think so. I think it's just really their tail that will change, and it's really what's happening is the sun or the comet's going to melt a bit, so it's going to. I think the closer it gets to the sun, really the outer layers start to burn off, so its mass will change, so its orbit will change. So eventually, it probably will change the orbit of the comet, but I think it has to be quite close to the sun for that to happen. But really, its orbit is determined by its mass and its orbit around the sun. So I don't think the flares really change the direction. I think they just probably have an interaction, or they blow off the tail. Essentially, is what happens.
And everything we see there is just plasma. There's nothing as solid as an atom.
Well, the plasma. So yeah, okay. So there are actually heavier elements in there. So a lot of what you see is the energetic particles, and you actually see ions, and I think you see helium enriched things. So you see the heavier elements. They're smaller. Yeah. So that does get blown out as well. And you see basically what the filament is that forms the core of the CME is chromospheric material. So you're getting all the stuff that's in there. It gets up into the prominence, and then that blows out. So you start to see that as it arrives at the sun.
I've forgotten what CME stands for.
Coronal mass ejection.
But it doesn't say what's ejected.
Well, the plasma is
plasma.
Is plasma. But there's also heavier elements and things all involved in there as well. So yeah, this is the nice and that's the same one.
Do those heavier elements reach the Earth too?
Yes, some of them do. And there's, I'm having a bit of a blank on that right now. That's not really my area, but you do see the enriched helium. I think you see, I forget what else you see. There are things that you see when they hit the Earth. So this is a nice movie, and I'll maybe need to wait till it goes back to the start. And it just really shows how how the solar wind and how the coronal mass ejections really interact with the Earth's magnetic field. So here we see a very basic CME. So here's the plasma. And the magnetic field is contained in that as well, so it's still twisted, because you actually see the magnetic field, we see evidence of that hitting the Earth as well. And it basically buffets the Earth's magnetic field, it pushes it back and makes it come up round about the back of the Earth, and then it pinches in behind the Earth, and you get this, what we call reconnection, where there's electrons accelerated, so the more particles are accelerated, they stream down the magnetic field, and that's where we get the aurora. So here we go, here's the CME. Here it hits the Earth's magnetic field. You can see it's pinched in over there, and this is the field that behind the behind the Earth. There's reconnection, and then these electrons are accelerated, and when they come down, they hit the Earth's atmosphere, and that's actually where we get the Aurora Borealis from. So, or the Northern Lights, as some people have heard of them. And we also get them in the southern hemisphere. It's not just the northern hemisphere. So here you can see here. So the Aurora Borealis are really just these ovals at the north and south poles of the Earth, where those electrons are coming down, and they hit. They come down into our atmosphere, and they interact with our atmosphere. I'll come to that a bit more in the next slide. I just wanted to show these movies first. So this is like the solar wind, and you can see how it's interacting with what we call, this is the magnetosheath and the Earth's magnetic field, and those electrons get accelerated and they come down and they make these ovals and they display big displays of light. So this is what you see when you see aurora. So you see these big displays of green and blue and sometimes red lights in the sky. And these things, you really need to be quite far north, it needs to be quite dark. And you need to have some sort of activity on the sun in order to get these. So there's been quite a lot of aurora recently, and certainly last week there was a chance of seeing them at lower latitudes. So let me just show you what causes the aurora first. So sometimes you get green, sometimes you get red, and sometimes you get blue. And this is because of what the Earth's atmosphere is made up of. So most of the time, most of the atmosphere is nitrogen, and that gives you the red and the blue colours here. Then we've got 21% is oxygen, and it gives you the green. Now, the green aurora are actually the most common, and the reason for we actually get more of the green oxygen aurora than the nitrogen is because when the accelerated electrons come down the magnetic field lines into the atmosphere, what they do is they hit the atoms, and in the same way that the atoms become ionized, they don't become ionized, but what happens is the electrons around about the atom, they get a bit of energy, and when they get energized, they have to lose that energy again at some point, and when they do that, they emit these lights at these colours. And so the reason that happens in oxygen is when the electrons round about the atoms in the Earth's atmosphere get energized, basically they lose that energy again really quickly. Whereas in the nitrogen's case, the electrons get excited, but then they sit there for a while, and so the nitrogen can kind of dissipate, and so when eventually it does give out the blue light, they've all kind of dissipated. You don't see this blue emission as much. So the thing about the Northern Lights is they're actually quite high up. So here's the plains, you can see weather balloons, Mount Everest. However, they are below the shuttle, which means that from the international, they're below where the shuttle flies, and also the International Space Station. So it means that you can actually see the aurora from above the aurora from the International Space Station. So these are amazing movies. So here you can see the red and the green, and we're flying over, and you can see where all of these electrons from the solar wind are coming down and hitting our atmosphere, and this is what's causing these lights. And what you're actually seeing is you're tracing out the ends of the magnetic field. So the magnetic field that comes in around about the Earth's atmosphere, they're all ending down where the aurora is. So you can see this nice glow. I just think these movies are amazing.
So I see the red and the green there. I didn't see any blue.
Yeah, the blue is just difficult to see. This one. Is this one? Yeah, I think these are amazing. You can see at different heights in the atmosphere where those electrons come down to in the atmosphere. And you see that they're not static, they're very dynamic. They move around, and you can just see all the effects of the magnetic field.
Is that flashing real, or is that an
Was there flashing down somewhere here in the clouds? Was it something down? Those are thunderstorms. So you actually think thunderstorms from the International Space Station. I think it's this one that's the best one, actually. I think this is actually San Francisco that you see. Yeah, it is. So this is actually the Bay Area, I think, here. Maybe we passed the Bay Area, and then there's Los Angeles. This is Baja, and down into Mexico. And you can see all these thunderstorms as well from above. And then the lights, the cities. So yeah, I should probably finish up because that's about 12 o'clock. So I will add a few more slides actually just to finish. This is something that you might want to know if you ever want to go and look for aurora. You want to know where to see them. This is a map, and it shows you what we call the KP index. So if you're down here, you need a KP index of 9 in order to see the aurora. If you're higher up, you need lower levels. So up here, you only need a 3, and there's a good chance of seeing aurora. So you really need to see really nice aurora. You need to be further north, so there's more chance of seeing them. So the idea is the stronger the KP index, the more that's a really powerful geomagnetic activity that means you can see the aurora. So this is actually for tonight. So you can see that a couple of days ago we had a KP index of about 6, and then now things have calmed down a little bit. We've got about 3. So you'd really have to be up in Alaska in order to see these aurora at this time right now. But I think there was one occasion in 2004 where the KP index went right up to 10, and they were able to see aurora down in Oklahoma. So every now and again there's a chance, but you still have to have clear skies, no clouds, and you want to get somewhere away from city pollution, from light pollution, from out all street lights, everything. Get as far north as you can and get somewhere dark, and there's a good chance of seeing them. So I'll leave you with this, and this is where we expect to see aurora tonight. So unfortunately we're down here. So. Yeah, Scotland might get something. I've never actually seen an aurora so far. But keep an eye out for them if you're flying, because if you're in a plane, sometimes you can see them. So that's really cool. Sit in the north side of the plane, and you might have a chance of seeing them. Okay, so I'll finish there.
Thanks. More questions?
So one thing you didn't talk about is, I guess, what I would call solar climate is long-term changes. Like there was the so-called solar minimum.
Yeah.
And I'd just like to hear if there's anything current on what people think might be going on in the long-term changes.
Long-term on the sun, or do you mean by long-term effects on the Earth?
Well, long-term in the sun, because
So,
changes
yeah.
in the sun affect the Earth.
Yeah, so there's the 11-year cycle, and then I've seen 1 or 2 talks recently about how there might be this global, maybe 100-year cycle of where the sun is more active or where it's really not. I think way back in the 1800s or something like that, there was what we call the Maunder minimum, which was where the sunspot cycle essentially stopped. And I know that our famous example from the UK was that the Thames froze over, that it was that cold. And so there's no sign of that happening yet. There is a lot of research going into this, but it's incredibly difficult to really predict that far in advance. One thing that I know there was one press release maybe about a year ago that was saying that sunspots were getting weaker magnetic fields, so that sunspots were maybe not going to be produced in the next, I don't know, maybe 3 or 4 solar cycles, that maybe sunspots just wouldn't be strong enough magnetic field to cause the sunspots, which means that you're not going to get the same flaring activity. And that's, I think right now where we are in the solar cycle, we're right on the edge where we know what's going to happen. So I think we're at the stage, so in the last solar cycle, where we are right now, we're at the same stage as what we were in the last one. So it could change, that doesn't make any sense. Trying to explain more clearly. Where we are is no different from the last solar cycle, but there's hints that it could be different. And so I think we still need to wait another couple of years to see what's going to happen with this solar cycle, to really see whether this is going to be significantly weaker, whether there's going to be less flares, and then what that means for the overall global changes. But I think we're right on that
What about really long time? Like, is the solar constant change, over billions of years?
Over millions of years, it's eventually going to change, because the sun's eventually going to change. So I think we're, another few billion years before we start to burn helium. But yeah, I guess we need to start to look to other stars and other things to really see that, because we're not going to be around long enough to see it. But that's why we look at things like the Hertzsprung-Russell diagram. So we look at a whole spread of stars, and we can see what's going to happen essentially from similar stars to our sun. I don't know. I'm not an expert in that. I haven't looked that far in advance. Yeah.
So I wanted to ask more about what's happening in the interior of the sun. You touched on it a little bit at the start of the talk. Wanted to get a better idea. Do we know over what range fusion actually takes place, and what happens when we're outside the fusion range, but well below the surface, other than the energy scattering around?
So that's still. So that's sort of quite an active area of research right now. So the core is really defined to that sort of inner fifth of the solar interior.
You said the inner fifth?
It's like the inner fifth. It's like 0.2 our sun is like the core. We know something about the interior of the sun because there are waves that travel through the sun. So basically, if something happens on the sun, like on the surface, this is like the magnetic field changes or something, it launches these plasma waves, and they propagate down into the solar interior, and they actually come back up elsewhere. So it's kind of like you see these ripple effects, and you can tell something about the nature, what we call some of them we call sunquakes actually, and you can see these ripples going off, and you can tell something about the frequencies and how far away from the main disturbance that occurs. You can tell something about what's happening in the solar interior. And I know there's a lot of study into what, like, the solar dynamo. So the solar dynamo is the thing that causes the magnetic field. And so really what happens is you've got your inner core, you've got your radiative transfer zone, and then you've got a convective transfer zone. And the difference between the radiative and the convective zone is where, right at the base of that is where they think the magnetic field is generated. So this stuff in the middle is rotating as a solid body. The stuff on the outside has got differential rotation, and so that's what causes the generation. We know a fair amount about it, but they still don't understand the solar dynamo. Like, the parameters that they have in the models are kind of a bit wonky, and it's not really what we're seeing, so, yeah.
What about, so the fusion takes place in the core, in the inner 2/10 of the radius in the sun's case. Do we know much more about that than just that the fusion takes place there?
I don't know, actually. It's not something that, the main things that I've seen a lot of research on is really about the solar dynamo and the solar interior.
We know that different stars have different power sources.
Yeah.
Basically, when the sun has the PP chain.
Yeah, that's true. Yeah, we know we know that the solar fusion, that fusion happens in terms of what we call the proton-proton chain, and then there's a CNO chain, and that generates the energy. But I don't see many talks about that that deep in the corona, in the core. Sorry.
But you think the core would be rather homogeneous, even if it's very turbulent? It would be sort of more or less the same.
I don't know.
One part as the other.
I actually don't know. I mean, the sun surprises us in many ways, so I don't actually know because the difficulty is probing that far down. So these waves that propagate in and come back out, I think they only really
Even
go down.
Superman doesn't go down.
Exactly. So there's one mission that's coming up in the next 10 years that actually the lab is going to have part in building one of the instruments. It's called Solar Probe. It's just going to fly straight at the sun. But I mean, it's not going to get. It's not going to get that far. I think it gets to like maybe like 1/10 of the distance from here to there. But well, 1/10 away from the sun. So it's going to go 9 times closer. But we're not going to get to the core. So I think we don't really know for certain.
All inference.
Yeah.
Are all stars on the same basic model? Not some stars, don't they rotate the same?
So some stars are different. It depends on the mass. And so like what I've really been talking about is really like the sun. Some stars I believe have they have the core and then they have a convection zone and then a radiative zone. So they have it the other way around. Some stars like the ones up at the top of the Hertzsprung-Russell diagram, the high mass stars, they burn fast, die young kind. They can turn into supernovae or neutron stars, which basically mean that they become really dense, and so they just sit there. That's disastrous. So they're completely different. And then the ones down at the bottom end, we don't really know what's going to happen to them because their lifetime is so long.
But do they all have magnetic fields because of the way they are?
Yes, I believe so.
Planets.
No, planets don't. So really, what you get, so what happens? There's a subtle point where you either get a star or a failed star. So the gas clumps together, and you can get these things called brown dwarfs, which basically don't have a high enough temperature or density for the fusion to start, and they basically just sit there being not fusing, and they are about 12 times the mass of Jupiter. So Jupiter is almost considered to be, well, it's not a black brown dwarf, but it's the same sort of size and idea.
Where were they on the main scene?
They were right down the bottom. So the brown dwarfs, I believe. Yeah, I guess they're not really stars, so they're not on the main sequence because they're not burning fusion. But for the magnetic field, you really need a core. You need some way to generate that field.
And it has to be slipping a little.
Yeah, I guess that's the current theory. I mean, the Earth has a magnetic field because we have a molten core. So.
The point that you mentioned is the idea that you're going to send it into the core of the sun and it'll emit data that it gathers as long as it can until it's destroyed.
Yeah, essentially. So we're not going to get to the core of the sun, but we're going to. The big question is, will Solar Probe Plus? Because actually this was proposed many years ago, but this is the new updated version. But it's going to see whether it can actually get into the corona, and that's actually one question that we're going to start working on is, will Solar Probe hit the corona? And there's going to be a big shield. So most of the instruments will sit behind the shield, except one little one which will peek around the edge. Not sure how they're going to do that, but yeah.
What determines when fusion of hydrogen changes over to the fusion of helium?
Essentially when it runs out. So there becomes a point where all of your hydrogen has been converted to helium, and you just then start to fuse the helium.
Are you not having any helium fusion during when hydrogen is fused?
I think it sits inactive until a certain point. I think it sits in the middle being inactive until a certain point. You probably need some change in the conditions in order to start fusing the helium.
What are they going to make that shield out of, Saran?
I don't know. That I actually don't know.
You talked about the electrons affecting the Earth's magnetosphere. What happens with the ions?
Unclear. This is I'm more of a flare person, but I would think you probably get some similar interactions or something. I don't know.
Do the magnetic fields of the sun interact with the Earth's magnetic fields in a way that spins up our dynamo or spins it down?
I don't think so. Really, what you get is our magnetosphere just gets kind of buffeted around. So our magnetosphere really protects us from the sun's atmosphere and all these influences. And so what basically happens is it gets pushed back, and that's what can affect the satellites, is the Earth's or the sun's magnetic field and the energetic particles.
In a previous lecture, they said the magnetic field of the Earth was going down, disappearing over 100 years.
No, I don't know.
Yeah, for sure.
I think there's a worry that the Earth's magnetic field did flip polarity, which it does. I think that's more like on sort of million-year time scales. But during that flip, we may be lacking that magnetosphere to protect us from solar activity.
I think I thought it was like 10,000 years or something like that. But you see it in rock formation that the Earth's magnetic field does change, and so I'm not really sure what happens when we're in that change over. I don't think it happens just like that. I mean, it's a slow
It's the
process,
idea
so
that
maybe there's
we've
some.
been vulnerable. Setting up a bit more sunscreen on.
Yeah.
Is the MHD bundles good enough to capture the dynamics of just one flare? You said the dynamo bundle is not good enough.
That's kind of a political question. I think no, not yet. I think there are aspects that we can model really well. I think that right now, to do the magnetic field extrapolations from what you see in the photosphere with MHD, I think that you see sort of the simpler features of the field, but you don't always see the shearing and the twisting. And there's still a lot of, even between different people's models of the same flare, they appear slightly differently depending on the method. So, yeah, yes and no.
To sustain that magnetic field, we have to have significant amount of volume current circulating. Are the ions and electrons counter-moving to sustain that magnetic field? If so, what's driving them? Is the time rate of change of the magnetic field driving the ion motion?
In solar flares?
Well, you have this magnetic field, something has to create that magnetic
Yeah,
field.
yeah,
So
right.
you have to have current circulating.
Yes, right.
Below the surface. So is that current mostly electrons or ions, electrons counter-moving?
I don't know actually. I just know that it's really that there's this. Well, it's because of the solid body rotation in the radiative zone and in the convective zone. So all this plasma is flowing against it. I don't think that the ions will be. Well, maybe they are flowing in a different direction. I don't know. I'm not a solar interior person, so.
I was going to ask how you got into this field. What made you decide to?
A lot of people always say they started looking at the stars when they were younger and stuff. I actually just always chose subjects that I wanted to do in school, and I somehow ended up being a solar astronomer. So I always enjoyed like physics and maths and things when I was in school. I did that at university, and then one summer I did a summer project between my third and fourth years, and it was on solar physics. And we were looking at these things called solar tadpoles, and above flares you see these bits of plasma, these voids wiggling down, and they were called solar tadpoles. And that just for some reason just caught my imagination, and from then on I was like, ooh. With the sun, I guess you have so much data. Like everybody in my year wants to be a cosmologist because that's where all the exotic questions about where the universe formed and stuff. And I just thought, why would you want to do that when you get 5 points in your graph? I want to be able to see the sun and get nice movies and get good information and not be defined by the statistics. I wanted to see, actually see what I was looking at. So that's really, I guess, why I chose solar physics, just because I thought it was fascinating to look at these things. So that and the fact that the sun is still huge, that's my number one thing. I just still can't get over that. So.
Thanks everyone for coming, please.